So Richard Beanland, after undergraduate degree in physics, took a PhD in crystallography of interfaces at University of Liverpool, focusing on epitaxial layers and semiconductors, graduating in 1991. After several years of postdoctoral research assistant, specializing in transmission electron microscopy, both in US and UK, Ohio State University and Liverpool once more, Richard moved to industry to work in the research center of GEC Marconi, mainly working on electron microscopy of semiconductor materials and functional ceramics. In late 1990s, the company focused almost exclusively on 3-5 element optoelectric devices, means utilizing compounds formed between elements of group 3 and group 5 of periodic table. Then the company went through a series of changes, being sold and taking over Nortel optical components, finishing as a 3-5 fabrication facility. Richard left in 2007 to become a research assistant once more in the Department of Metallurgy and Materials at the University of Cambridge, before finding a place in the Department of Physics at the University of Warwick in 2008. Since then, Richard has developed his research interest in electron diffraction, functional ceramics, and semiconductor materials. Today, Richard will present his lecture entitled Exploring Dynamical Scattering Using Digital Large-Angle Convergent Beam Electron Diffraction Patterns. Richard, the screen is yours.
Thank you. So yes, I'm going to talk about digital large-angle convergent beam patterns. So these pictures here are the kind of patterns that I'm talking about. This is experimental data. This is from a crystal of lithium niobate. And all of these really incredibly intricate patterns that you can see are dynamical effects, looking down the zone axis of a relatively thick crystal. You can see it looks very complex and very beautiful, and you might also think very difficult to understand. But there is useful information in here, and that's what I'm going to talk about. So I like to make this metaphor about the way that people tackle doing structure solution and now structure refinement using electron diffraction and X-ray diffraction. So of course, X-ray diffraction has been around for a very long time, and there's lots of sophisticated tools to do that. And my metaphor is that from a distance, sheep and goats look pretty much the same. All you see are a load of white dots off in a field somewhere. It's only when you get up close that you can tell the difference. And it's the same with electron diffraction and X-ray diffraction. From a distance, they look very similar, but once you start getting into the details, then you realize that they really are quite different. So it's becoming less and less the case, but it still is the case that we are using methods developed for sheep, that is kinematical diffraction theory, on our goats, which are really very dynamical. And it works to a great extent, but really we should be using goat methods. We should be using the methods appropriate to the technique that we have. Now, if you're using kinematical theory, you're usually describing it diffracted intensities as the structure factor times its complex conjugate. Well, we know this is not correct for electron diffraction. As you saw in that very first slide, those intensities are changing all over the place. And so there's obviously something much more important than just the structure factor here. So we'll have a look at the dynamical diffraction effects in some more detail now. Going deep into goat territory, if you will. And I'm going to start off with convergent beam electron diffraction. So this is a beam that is focused to a small point on your specimen. It's got a range of angles coming in. This half angle here, alpha, describes a convergence angle. And of course, when you've got a thin specimen, you're going all the way through it with something like 200 kV electrons. And what comes out the other side is also a cone, an expanding cone. And every time you get diffraction, each diffracted beam is also a cone in shape. So when you look at a convergent beam electron diffraction pattern, what you see is a set of disks. And you have a direct beam disk, a circle disk, and then you also have each disk corresponding to different diffracted beams. Now, when you start looking inside these disks, you see you have these variations in intensity. So these are dynamical diffraction effects, and these are due to multiple scattering. So these have been known for a very long time. The symmetry of the patterns was worked out in the 1970s. The restriction that we have here, one difficulty we have here, is if you want to be able to see this detail in the disks clearly, then you can't have this incident beam half convergence angle bigger than the smallest Bragg angle in your diffraction pattern. So that really limits how much of this dynamical diffraction pattern you can see, because once you get too big, everything starts to overlap. So when I first started working on this, I realized that what you could do instead of just taking one pattern was to take lots of patterns over a range of incident angles, and then use that to reconstruct and actually see a bigger area corresponding to these disks. Okay, so here's an example. This is using the script that I wrote to drive the microscope and collect pictures. I think it's going to collect about 2,500 pictures here, so 2,500 convergent beam patterns. I'm going to tilt the beam backwards and forwards in a raster pattern as we go backwards and forwards down here. And I'm going to put on the right, I'm going to output the intensity corresponding to one diffracted beam, which is this one here. So at this particular orientation, it's a long way away from the Bragg condition. But you'll see as the beam goes backwards and forwards, we'll cut through that Bragg condition, and you'll start to see the diffracted intensity. Okay, so here we go. Okay, so you can see what we're doing here is we're cutting through the Bragg condition. The Bragg condition runs down here. And you can see the intensity that we get out. Well, it depends very, very much on exactly what the incident beam orientation is. And you can see we're building up this really rather complicated and beautiful pattern. You can see there is some symmetry here. So this is a highly symmetrical crystal. This is barium titanate. So you can see you've got mirror symmetry here, you've got mirror symmetry here. So this is one of the ways to look at the symmetry in the material. And all of these variations in intensity that you see are effectively caused by multiple scattering. And that multiple scattering encodes the interference between all the different diffracted beams as they go through the crystal into intensity here. So it's not just the atom positions, but everything to do with the electrostatic potential gets encoded in these intensities. Okay, here's another example. I call them digital large angle convergent beam or D-LACBED patterns because you can only really get them with computer control. Again, here's given a comparison between a spot pattern that you get with a parallel beam, a convergent beam pattern with a convergent incident beam, and then the difference between that and your LACBED data. So I'm going to take that, put it up, and spread out so I can get all the other diffraction patterns in. And you can see the data that you could see was just one small selection of this really big, complicated data set. And again, you can see symmetry here, for example. So this is gallium arsenide. It's a 1-1 ozone axis of gallium arsenide. It's a semiconductor, a 3,5 semiconductor material, and it's non-centrosymmetric. And in a non-centrosymmetric crystal, plus G and minus G give you different intensities in dynamical scattering. So, for example, over here and over here, these are plus or minus G, and you can see they're rather different. You can see here and here the same, and that's because there's a vertical mirror plane. So you can see the symmetry very easily, and that's very nice. But I was really interested to see if there's anything more quantitative you can do with this kind of data. So to explore that, I've written some block wave simulation code. So I'll just very briefly talk about block waves. You take your crystal potential and you describe that as a 3D Fourier series. Okay, so that's here's your crystal potential. Here's a Fourier series describing it. You generally actually take out this factor h bar squared over 2m, because we're going to put it into Schrodinger's equation, and that's a factor that if you take out now makes it more straightforward. So you end up with these, rather than VGs, they're known as UG Fourier coefficients. These Fourier coefficients can be complex. So the imaginary part describes absorption, which is non-Bragg scattering, or scattering that is lost from the block waves. We describe the transmission wave function, so the wave function of the transmitted electron, as a sum of block waves. And the block waves are also themselves a sum of plane waves. So here is a block wave described as a sum of plane waves. The block theorem says that you only need to consider Fourier components that are the same as a reciprocal lattice. So that simplifies things a lot. And then you have each one of these block waves, you then add them all together with various different weights, and that gives you your total electron wave function. So it looks fairly complicated, and I suppose it is really complicated in that you've got two infinite series that you're equating to each other. Once you've got into Schrodinger's equation, you can organize this as a set of simultaneous equations. Each row corresponds to a different G vector or Fourier component. You can have the Fourier components of the potential, and C is an eigenvector of A. And the key thing here is that down the diagonal is where you encode the crystal orientation. And crystal orientation gets encoded through the relative component of the K vector and that perpendicular to the surface. And there are fairly standard ways to solve these kind of equations. If you take the complex exponential and multiply to post-multiply by the inverse, you can end up with a matrix equation where you can get the intensities out. So anyway, yeah, I won't go into any more detail. The main point to take away here is basically you're just solving a set of simultaneous equations with complex coefficients. And you're solving a matrix of size n by n, where n is how many diffractive beams you're putting into the model. And you can do it using standard computing methods. There are algorithms that will solve these equations for you. But the time it takes scales as n cubed. So the more beams you put in, the slower and slower it gets. And so one of the questions is, well, how many beams do you really need? And like all good answers, the answer is it depends. Here's a plot giving you an example. So what we have here is doing one simulation with a certain number of beams, and then doing another simulation with a different number of beams, subtracting one from the other, and seeing what the difference is. And you'll find, of course, as you put more and more diffracted beams into the calculation, your simulation gets more and more accurate. And it actually gets accurate exponentially. You can see this is a straight line on a log plot. So the more beams you put in, the more and more accurate it gets. And what we have here is the maximum difference in any pixel in one of those LACBED patterns. Okay, so this is 10% difference, 1% difference. Down here, that dotted line there is what you would call 8-bit, 1 part in 256. So you can do a set of simulations with different numbers of block waves, and you can see exactly how many you need to include to get down to the accuracy that you require. Now, each incident beam orientation in a LACBED pattern corresponds to 1 pixel. So we have to do this calculation on a pixel by pixel basis. And you can, one CPU can solve a 200 block wave problem in about 150 milliseconds. So when you've got 10, 20,000 pixels in an image, then this is getting very slow. So I speed things up by using parallel computing. So the amount of computing resource available to people in academia nowadays is really incredible. You know, there are plenty of high performance computing clusters around that you can get access to. So we've got one of the UK's mid-tier systems, Avon, which has got over 8,000 cores available. So I can throw a huge amount of computing power at this problem very easily. So this is a simulation of 320 by 320. That's over 100,000 pixels. And that only takes 1 minute if I'm using 400 cores, 200 beams. And you can see there is actually now a very good correspondence between experiment on the left and simulation on the right. There are some differences which I'll get to in a minute. So now that I can actually simulate these patterns, the question is, well, what is it sensitive to? What happens if you take some parameter and change it? How does that change the patterns that you simulate? And can we actually do a fit to experiment? So I may actually, I'll put some caveats in a second, but there are 7 main things that you can, that you're sensitive to on the sort of macro scale without going into the structure factors themselves. The first, when you're simulating a pattern of a certain angular range, the most important one is actually what the angular range is. So that's nothing to do with the material, it's just the simulation. The next most important thing is actually where the atoms are. Where the atoms are makes a big change to intensities. The thickness of the specimen is also important because that determines how much interference you get as the waves propagate and what the balance is between them all. The next one down is occupancy. Now I've called this occupancy, but actually I suspect, having seen Paulina's talk, that it's not occupancy. Occupancy was the only knob that I could turn because I'm using an independent atom model. But I suspect that could well be charge rather than occupancy. Fifth one, lattice parameter. So if you change the lattice parameter, you change the distance over which the waves travel, and that also changes these interference patterns. The voltage that you're using, the accelerating voltage, is actually not, surprisingly, a huge change. I mean, it does change things quite a bit, but it's not anywhere near as important as these other parameters. And then finally, you've got your thermal vibration effects, which smear your potentials out, and that also has an effect on the patterns. And well, what effect does it have? Here we have a set of difference images for different reflections. So this is your direct beam, a 114, a 228, and a 3312. I think this is from Sapphire. And in these images, if it's gone orange, then it's a positive difference. If it's blue, it's a negative difference. And the brighter orange it is, the bigger the difference is, or the brighter blue it is, the bigger negative difference it is. So if I take my original model and change the convergence angle, then obviously that makes a big difference to actually where the lines are, so that's quite a big difference. If I take my original sample and I move one atom by a certain amount, then these are the changes in intensities that you get. And you can see you get these complicated changes of intensity. Some places get brighter, some places get darker. In each reflection, the bits that get brighter and darker are different. So it's quite a complicated pattern. If I change the thickness of the crystal, then again, I get another complicated pattern where some bits are getting brighter, other bits are getting darker. But the key thing here is this complicated pattern is actually different to that one. So the changes that they make to the pattern are actually very different. Here's occupancy. Again, this is different again. Some of them you might look at them and say, well, actually, this one looks very similar to that. But when you get down to other reflections, they look completely different. So it is for all of these different parameters that you can change. Each one has a unique fingerprint of changing intensities on your dynamical diffracted data. So what this means is they become effectively independently refinable. So although the patterns themselves are very complicated, because each parameter has a unique fingerprint, you can just refine them individually. So we started off doing some very simple tests, trying to find the simplest examples that we could, just to see how these things happen, how it behaves. And the simplest thing that we could think of was a face-centered cubic material like copper. And here, really, there's very little that we can do with face-centered cubic material. The only thing that changes is the thermal vibration. So we can look at this copper as a function of temperature. These are some D-LACBED patterns looking down the cube face. That's your direct beam. These are the other diffracted beams. And what happens when you change temperature, mainly in electron diffraction patterns, is that you increase the absorption. And absorption is very strong when you're aligned to crystal planes. Here you've got the 220, sorry, O20 and O40 diffraction conditions line up here. And you can see as you increase the temperature, this just gets darker and darker. And what's happening here is this is all turning into diffuse scattering in between the Bragg beams. And you can see we have the same kind of thing in simulation and experiment. And if we just take one particular experimental data set and we compare that against simulations done at different temperatures, then we find we just get one minimum. So right, we only get one answer. This is what we expect our thermal vibration by Waller factor to be. And you can see that as we change temperature, these increase, they should do. So it seems to be working. If you compare to what people did in the past, so the black and white data is from X-ray diffraction and neutron diffraction and various other methods. And the stars are our data from two different directions looking down crystal, and you can see it's really a great fit. You know, it fits exactly on that curve. No free parameters or anything, we just fitted it, got a B factor, and it seems to be the right answer. So that was very, very gratifying. Going back to gallium arsenide, another pretty simple material. And again, there's not much you can refine here apart from thermal vibration parameters. Here are the changes in your direct beam and your OO2, OO4, etc., etc. If you change the gallium Debye-Waller factor by 7%, you get changes in diffracted intensity up to 5%. And again, you get this very complicated pattern of some bits getting brighter and other bits getting darker. This is again a difference. Which, if I make the same change for arsenic, well, we get a similar magnitude, but again, the pattern's completely different. Okay, so you can see gallium and arsenic completely different, which means again we can refine them effectively separately. So it doesn't really matter where you start from, you end up with one nice global minimum that you always converge to. And you can see at different temperatures, we've got gallium and arsenic Debye-Waller factors, and they both move, and it's a reasonable answer, it looks like. Except this is the answer that we always converge to, and this is the X-ray answer. So it seems everything that I've done apart from copper, we also always get much larger Debye-Waller factors from electron diffraction using this dynamical refinement than is seen by X-ray. It's always larger all the time. And what's the reason? Well, I think this is down to the independent atom model, actually, and I think what we're seeing here are indeed bonding effects. So if you look at my best fit simulations here, so this is experiment on this side, this is simulation on this side. You can see, okay, plenty of this, it's a good fit, but there are certainly bits here which do not fit very well. Right? And the only thing I've got left to change here is a charge on the atoms. And so that bonding between the atoms is presumably the origin of this difference here. Here's the same kind of thing, experiment, simulation, and another reflection. And again, you can see there is a difference here. There's a noticeable difference. So I suspect that's due to charge. It could be possibly due to anharmonic thermal vibrations, but I think charge is much more likely to be a bigger effect. Okay, moving on to what else you can get out of these patterns. As I said, it's mostly sensitive actually to atomic coordinates. And so here's an example where not all of the atom positions are completely determined by symmetry, but still fairly straightforward. So this is sapphire. Sapphire has plenty of atoms in its unit cell, but it's only got 2 free parameters in its structure because the aluminium lies on the threefold axis, so that can only move along Z. And similarly, the oxygen has only got 1 degree of freedom, that can only move along X. So we've only got 2 dimensional refinement for atomic coordinates. So this makes it fairly straightforward. Here's our digital LACBED data covering lots of different reflections, and again showing all these complicated changes of intensities. And if we refine those patterns against simulation by varying atomic coordinates, then we get a pretty good fit. Okay, so this is the best X-ray study that I can find for atomic coordinates of sapphire, and this is ours. You can see it's definitely outside their error bars, but in absolute terms, it's not that bad. So we're 0.4 or 0.2 picometers away from the best accepted structure. And again, we've got 1 global minimum that we get to by refining against this. So it's a very robust method, it seems, and it seems it's also reasonably accurate and precise as well. Okay, so those were really simple materials. So we thought we'd try doing something a bit more complicated. Now, as you know, my background is not in molecular materials. I'm more into ceramics and semiconductors. This came up as being an interesting possibility, this calcium manganate. It's a Ruddles and Popper material, so it's blocks of perovskites which have got a rock salt stacking fault, which occurs every 2 unit cells. So you get this shift between each perovskite block. In the perovskite structure, you've got these oxygen octahedra, and these oxygen octahedra can tilt and rotate, usually described by distortion modes. And in calcium manganate, you get both a combination of a tilt and a twist. You've got 2 different modes going on at the same time, which give you this multiple set of displacements of the oxygen atoms. It's also a little bit complicated in that you can see you also have some stacking faults here. So here it should be just 2 blocks, but occasionally you get the 3 block. We have to make sure that if we're going to go investigate this structure, we have to really go in on the nanometer scale. And of course, you can do that with focused electron probe. You can get down into something that's only 20 nanometers and say, I'm going to sample this. When you refine the structure, again, it turns out that pretty much everything can be done independently. So all of the patterns, even though the patterns are very complicated, each atom refines independently. We were able to some extent, quantify just how accurate they are. So you can see you get varying accuracies depending on which atom it is. Generally, the higher atomic number, it seems that the more accurate it is. I suspect these are exactly the same as X-ray diffraction or even continuous rotation diffraction kind of experiments. And if I was to do this from scratch, it probably wouldn't take too long in terms of work. It probably could be done in a day. Just to give you an example of what the data looks like. So this is my experimental data. This is my simulation. And again, although I've refined the crystal structure very accurately, you can see there are still actually very significant differences here. For example, if you look at the 222 reflection between simulation and experiment, there's quite big differences between simulation and experiment here. And again, I suspect this is an ionic crystal. So I suspect, again, this is due to charge transfer between the atoms. In fact, if I refine the occupancy in this material, I get the oxygen occupancy always goes down to about 95%, which physically isn't reasonable. There's no way there's 5% oxygen vacancies here. And the calcium and manganese always goes over 100%. So this must be due to charge transfer. Just giving you a feeling for just how strong the effects of we might call absolute structure or non-central symmetry might be. Taking particular reflections, we find that they can be really very sensitive to this non-center, this lack of symmetry. So if this was the tetragonal structure, there would be a mirror plane here. And you can see these are Bouguereau pairs. These reflections are just very, very different. And the same for these 117s, they're just completely different. Here are simulations which also show a similar degree of difference, although as I said, I just don't quite get exactly the simulation to match the experiment. This is at room temperature. As you go up in temperature, so we can do this as a function of temperature, then you can see these start to change. And again, we can get a best fit simulation. And then you can see at 200 degrees, suddenly everything pops into being symmetrical. Okay, so what that means is, in this particular case, is that one of these distortion modes, the distortion mode which makes it non-central symmetric, has gone down to 0. But the other distortion mode is still present, and it stays there all the way as we go up in temperature. There's 300. Then something really weird happens at between 300 and 400. You get these big changes of intensity, which initially I thought must be due to these distortion modes, but no. Actually, the oxygen atoms are doing something very strange. You see the oxygen atoms, their thermal parameters are actually decreasing as a function of temperature up to a certain point before a high temperature or going back to normal. So there are some interesting structural things that I can see there, which I don't understand. Okay, let's try not to go on too long. So very briefly, I'm now starting to look at this structure solution and continuous rotation diffraction. So this is continuous rotation diffraction data. Again, from the simplest thing we could think of, which in this case is silicon, nice, completely defect-free piece of silicon. And this is a continuous rotation diffraction data set. It's about 1,400 frames done on a J2100 PEM. You can get this data very quickly, actually, and this data took less than 20 seconds to collect. Now, in this kind of data, it's very difficult to see, the dynamical effects, because all you're really seeing are spots. You can certainly see diffuse scattering data, right? So you can see the inelastic effects. You see these Kikuchi lines going through here. And I think these actually cause problems in actually measuring things like integrated intensities when you've got these lines going through the spots. We took these data and we used Lugrash's PETs to extract the intensities from every frame and also extract the crystal orientation. And then we used that as an input to our simulation program for block waves, so we could actually simulate this data using block waves. Here's the output from that simulation. So the previous, the computer program would produce square simulations because that was the kind of data that I was getting before. What I really want now is something long and thin. And the only way I could really get that quickly was to just make multiple simulations. So here they've got 70 simulations and then stitching them all together. So this is now almost 14,000 pixels wide by 400 pixels high. And I also had to make the simulations overlap so that if you've got a diffraction condition that goes across from one simulation to the other, you could avoid that. And I've got a new version which is almost ready that should be much better for conversion for continuous rotation data. So this is just the bright field, very, very large angle convergent beam diffraction pattern. This red line represents where the initial output from PET said the beam orientation was as you rotated it. And these are your frame numbers along the bottom. And you can see as you go through every time you hit one of these black lines, you've hit a diffraction condition. And so you produce a spot in the diffraction pattern away from the direct beam. Just looking at that direct beam in a little bit more detail, if you just take that whole set of almost 1,400 images and you just average them all together, and then just look at the center, and you can see that the straight through beam has got a Lorentzian profile. And if you take that average image and you go back to your stack and you divide that whole stack by your average image, then basically you normalize it. So that makes it easier to see what's going on in here. This is the normalized direct beam. And what you can see here course, are these black lines going across. These are your diffraction conditions cutting through your direct beam, and they'll correspond to a bright spot somewhere else. And in fact, we can see that if we take, again, this stack of 1,389 images that we've normalized, and then we basically take that stack and view it from the side, then you see this. So this is your direct beam intensity as a function of frame number. And you can see every time you hit a diffraction condition, you produce a dark line. Okay. And that's exactly what you'd expect if you look at one of these LACBED simulations. Okay, so this is your incident beam orientation as your crystal rotates, or your bad conditions move, and every time you cut through one, you hit. Every time you cut through one, you produce a diffracted beam. And also, again, you can see here the effect of absorption. So absorption gives you these dark bands between the lines, and particularly things like here where you've got some crystal planes that you really line up on, you get very strong absorption effects. Okay. So out of that data, there's about 1,000 reflections. And if you just look at each one as a rocking curve, so each green bar is the intensity that we got out of PETs. Well, most of them just look like simple peaks. So most of them you might think are kinematical. Out of that 1,000 patterns, only 27 actually showed something that you might say has got some structure that is definitely dynamical. So the question is really, how much difference does a dynamical simulation make? And how can we do that? Well, if we're going to do a dynamical simulation, we need to know exactly where we are in reciprocal space, because you saw from the previous work, exactly where you are can have a huge effect on the intensity of a diffracted beam. This is the initial kinematic fit, and you can see it's pretty bad. Mainly, well, not only because, but one of the main things you can see here, silicon, you have got lots of systematically absent reflections which have got zero structure factor, and they certainly don't have zero experimental intensity. So this is a big problem. And also you can see your strong beams are actually much weaker than you might expect, because they've all produced scattering into the other beams. If we just used dynamical intensities calculated from the rocking curves that we simulate using the nominal beam path, then we do a lot better. You can see we've got much better fit here. But it's still not great, right? There's still a huge amount of scatter here. And the reason this is not great is mainly because several other things have not been optimized. First, you've got to make sure that the thickness is right. So here is a plot of your experimental data. Actually, that shouldn't be experiment, this should be simulation as a function. Now that's experiment versus simulation as a function of thickness. So I'm changing thickness. And you can see some of these strong reflections really move backwards and forwards as you change the thickness. So it makes quite a big difference. And in some ways, this is similar to how LACBED patterns worked, in that individual reflections might be very difficult to interpret. But once you take the whole lot together, then it gives you something that is actually straightforward and simple and gives you a unique minimum. So you do actually get one unique minimum of thickness. Going back to the orientation, as your beam passes through reciprocal space, you'd expect it to be traveling along a straight line. And when you see each reflection appear, each diffracted beam appear, then you know you've cut through a diffraction condition. Now, when we do this simulation, we can see where each diffracted beam is. And so if we know, for example, that these two reflections appeared in frame 4, and then this appeared in frame 9, and then this reflection appeared in frame 12, then we should be able to work out exactly where the beam path is. But you can see in this particular case, these are the frames that the reflections appeared in, and you can see corresponding to the simulation, this is not a straight line at all. And that's because the orientation is slightly wrong. So each one of these steps here corresponds to about 0.1 of a degree. So we're a little bit off. We can actually optimize the orientation by taking this whole set of reflections and just shifting them backwards and forwards. So we know that this one always appears 4 frames after that one, but we'll just shift it backwards and forwards until we find the best fit. That's the result here. So here, this is the best fit to a horizontal straight line that I can get with these reflections corresponding to where their Bragg conditions are. You can see if I go a little bit further, then things get worse. So we can use that to optimize orientation. And doing that, we can see several things. One, okay, there was an error of, remember a frame is 0.1 degrees, so there's an error of a quarter of a degree in our crystal orientation from PETs. But you can also see that the offset changes through the data. And what that means is that the rotation speed of the crystal is changing. So it was going slower, and then it speeded up, and then it got quite fast, and then it slowed down again. And it also, in terms of the orientation, in terms of which row where we're cutting through the reciprocal space, that also changed systematically. So if we choose the correct beam path, having done this optimization, then that makes yet another improvement. So we still get to a better R factor. Taking account of the fact that your goniometer is changing speed. So here, when your rotation is going slower, then you're integrating for longer than you expect through a diffracted peak. And here, you're integrating less than you expect. That also makes another small change. And you can see each change that we make makes this fit better and better. Then finally, experimentally, we can look at each individual reflection. As I said, there are 27 that actually showed some dynamical data like this 311. You can see you've got this set of fringes here, and you can see also in the simulation, you'd expect it to do that. So that's your beam path. And you'd expect it to have a whole set of fringes. This is the intensity along that red line. And okay, you can see it's got some fringes, but you can see it doesn't look like that. It doesn't quite look like that. And the reason is because our incident beam orientation is not completely parallel, right? It's a Lorentzian. We showed it had a Lorentzian profile. So that means is you're actually sampling intensity off this red line, maybe not so much, but a little bit. And of course, because intensities vary an awful lot very quickly laterally, that can actually change intensities. So if you actually take account of that fact that we've got a Lorentzian beam profile and we convolve that in, then we get this, and you can see that is much better fit. And even actually in a single sharp peak like this, you can see that that turns into a Lorentzian profile, and that's actually much better fit too. Now, the detail that you get in this pattern also depends upon thickness. And so you can see here, varying thickness, you can find which is the best thickness that corresponds to this detail. So this is a rather different measurement than just taking all the integrated intensities. And it actually agreed exactly the same. So that was quite pleasing. It does seem there's various different ways to get to the same data. They're effectively independent and they agree. And that gives another small improvement in the fit by including the convolution. And then finally, in refinement, well, okay, it's a very simple material. The only thing we can refine here in the independent atom model is thermal vibrations. And so if we vary the thermal vibrations, we get one nice global minimum, and we get a much better fit. So this is about where we are at the moment. Well, I suppose we've moved on from here a fair bit. We're just about to have much better simulation methods where we can actually do this much more quickly. The main takeaway here is that, yes, dynamical diffraction makes a big difference to how well your fit is. I mean, that makes a big improvement. But there are lots of other things that you have to take into account as well to get a good fit to the data. And I'm sure charge transfer is also in here as well. Okay, I think that's more or less me. I'll say electron diffraction is superficially similar to more established methods like X-ray and neutrons. But really, if we want to be quantitative, we need to model electron diffraction correctly. I think there's actually a lot of opportunities here because the multiple scattering encodes phase information in the diffraction pattern. So although it's more complicated, I don't think there's a fundamental problem with diffracted intensities in electron diffraction. I think we can actually simulate it pretty well, certainly well enough to do a lot of interesting things. I would say a lot of the issues that we have solving crystal structures and getting a fit data is actually due to not having enough data, right? Not having enough frames, not having enough pixels. And those things are improving very quickly. So I think that's the main thing rather than lack of theory. You can see I'm putting caveats in here, by the way. And of course, electrons can get places up the techniques parts. They're very good at looking at very small crystals that you just can't access with X-rays. And there you are, electrons in places that other techniques cannot reach. And so, yes, be more goat is my main answer. Okay, thank you very much.
Thank you very much, Richard, for this beautiful lecture, really, which is now open for questions and comments. And we can see some.
I should keep that
chat
in case there's questions. Yeah.
So Paulina posted 2 information about conferences in the field of electron crystallography. Workshop at Antwerp, and also a lecture by Piero Macchi within the series of ECA, European Crystallographic Association launch webinars. Excellent. Piero will listen to it. And Daniel Carter, the difference between simulation and experiment with T remind me stops in high resolution transmission electron microscopy and CBD, somewhat improved by frozen phonon simulations using multi-slice. Is it correct? Is this correct?
Yeah, so just to put that into context for those people who mainly do diffraction. So Mike Stubbs was very famous at the end for standing up at conferences and complaining that when people tried to simulate high resolution images of electron microscope images of crystals, the intensities were never quite right. And they were off by about 20 or 30%, so really quite significantly. And it became known as the Stubbs factor. So there are lots of things that would contribute to a difference between simulation and experiment in electron diffraction. So block waves are really seen as the best way to simulate electron scattering these days by the electron microscopy community. One of the main reasons is the way that you deal with absorption is that once you have an electron that's been scattered inelastically, then you just throw it away. It's no longer there. But in reality, that goes into diffuse intensity, and that can then get scattered again and come back to be underneath the diffracted beam. So it can come out with the same K vector. So really you need to take into account that these inelastically scattered electrons can still end up in your diffraction pattern. So multi-slice does a better job of dealing with that, because you don't throw any electrons away. You actually take account of what direction they're going. So that was one big thing, and yes, that was solved to some extent by frozen phonon simulations using multi-slice. But it wasn't so much the frozen phonons, it was the fact that you weren't throwing electrons away. And then the second factor, which may be very significant for molecular materials, is inelastic scattering changing the coherence of the beam as you go through. So once you have an inelastic scattering event, you've lost the coherence of your electron, and so you don't get the same kind of interference going through your crystal. I mean, this might be why, for example, you can actually solve crystal structures for proteins using electron diffraction, when everything says that you shouldn't actually be able to do that using kinematical theory. So it may actually help you do kinematic simulations.
Okay. The next question comes from Ariana Lanza. Firstly, you have shown that the B factor can be refined precisely, but is always larger than the one found with X-rays. Could it be that the experiment warms up and charges up the sample quite a lot?
No.
And the second question is, anyway, B is known to serve as a trash bin of many unexplained errors, so the discrepancy may not necessarily be telling us something about the sample. There are many things that can blur and the electron beam. For example, could the optical distortion of the beam also be responsible for these discrepancies?
Okay, well, yeah, so to answer the first one now, the kind of beam currents that I'm using might change the sample temperature by quarter, half a degree, so no. And then part two, also, I don't think that this is, I mean, it could be, yes, there are maybe explained errors, and certainly things like changes in the electron distribution due to bonding will also change the effective size of an atom, just like thermal vibrations will. So there's, yes, there are lots of things that look the same there. But in terms of things like optical distortions of the beam and things getting blurred, well, no, because I mean that's Debye's famous result, isn't it? That when you have thermal vibrations, it doesn't make the peaks any more blurred; it changes their intensities. They're still sharp peaks. So it's not blurring of the pattern that we're looking at here. We're looking at changes in intensities.
Okay, thank you. Daniel Ugarte, do you understand what mechanical issue generates the somewhat oscillatory behavior of the angular positioning of slices that you associate to goniometer speed?
Yeah, I think it's just mechanical. So I've looked at some data from another gel microscope, and it actually looks to have exactly the same curve. And I think it's just inertia. So when you start off, it's a little bit slow, and then it speeds up. So I think it's just inertia. Yeah.
Michał Kamiński, hypothetically, would diffraction with polychromatic beam give similar interference effects?
Yes, although there I do think everything would blur out. We're not super monochromatic usually, but yeah, polychromatic beam, basically you're changing your Bragg angle, everything's going to blur out. but you'll have the same interference effects, yeah.
Leonardo Correa, how large is the beam tilt angle value utilized for digital LACBED? How many meters can you include in the refinement while still ensure no overfit or making all the process too slow?
Okay, well, as I said, so the beam tilt angle is limited by the quality of the microscope because you need to keep the beam in the same place. So this was done on an uncorrected TEM. And what happens when you get to a big beam tilt is actually your beam starts to displace from where it should be. So instead of being here, it actually moves. You actually have to shift it back. And also the beam shape starts to change. So more than about 3 or 4 degrees, and things start to go really not very nice in terms of beam shape and things. So that limits how far you can go with the beam tilt. How many parameters can you include in the refinements? Well, that calcium manganate had something like 40 parameters, and they all seem to refine independently and quite nicely. It took me quite a long time to do that, partly because I was developing the code. In fact, I would say it probably took me over a year. I don't know if that's too slow or not. It was quite slow. It's a lot quick. Yeah, now I've done it. It only takes an hour, but it took me a year to do it the first time.
Okay, Hansbeth, you mentioned that the electron diffraction data encode phase information. Would it make sense to compare this phase information with phases calculated from very high quality electron density models based on X-ray diffraction? Or did I misunderstood something?
No, that's exactly right. And that's where I was pointing out the differences, the very significant differences between simulation and experiment. I agree. Yeah. I suppose the only problem is that most of the materials I'm working on tend to be ceramics and things like that, whereas most of this seems to be done on molecular materials. But I'm sure there's a way of doing it. We can just find the right thing to work on.
Okay, thank you very much. I do not see more question, so let us thank Richard for this excellent lecture.